Okay. Oh, so, okay, so no one's here yet, but I mean, I still want to like use the full hour to sort of like start working on some problems. I think people will show up soon, but you know, I guess we'll see. So I basically just want to go over sort of like the so like some of the practice problems that I sent you guys. I do want to mention that while it is like a practice exam, that was from when it was in person, and not when it was what's the word? You know, during like over Zoom and like when it's all multiple choice online and everything, it's not proctored. So I would imagine that since it's not proctored, you guys can use your notes. The questions might be a little bit more challenging with regards to like theoretical stuff. But some of those multiple choice problems, such as like some of the ones we're going to be going over today, especially towards the end where there's a lot of graphs and it's like asking you about like continuity, differentiability, things like in some limits, things like that, and like what shit is true. Those are definitely, I would be surprised if something like that was not on there. And some of the other ones that we're going to be going over today, which you've probably already seen from like what Brett has sort of covered in lecture so far. I know he did like two different sessions of just review, so yeah. With regards to like other kinds of like material study, I think just going through like each section, sort of like understanding what kinds of problems could be asked for each section. You know, that one where there's like a piecewise function and there's like a constant there, and it's like, okay, so find the constant that will make this piecewise function continuous. That's like a big one. I definitely look at that, and yeah, so like that's like a type of problem, and that can those sort of things can probably be found for pretty much every single section. The earlier ones are mainly just like going over normal functions, so those might bleed into each other a little bit. So I wouldn't worry too much about that. Let's check. Awesome. So, I'm probably just going to get started on a problem first. And the first one I actually want to cover is the the piecewise one that I just mentioned. Oh, shit. Okay, yeah, I like definitely just have to like set my availability. Okay, I definitely just forgot to set my availability on academia. I'm probably gonna say this when people actually join, so hopefully it works. That's totally my fault. I totally just forgot to do that, just because this is like not a normal time for this thing. Hi, sorry, I forgot to set my availability on academia. Can you hear me? Okay, cool. Yeah, I just didn't set my. It's like a whole like schedule thing that I have to set up, and I just totally forgot to do that. So that was entirely my fault. But hopefully, like people can actually like join now. I sort of already gave it intro spiel, but I can sort of like restart it. You just have to wait a little bit for people to show up. Yeah. How are you guys feeling so far about it?
I'm nervous.
I can't hear you. It might be me.
Oh.
Oh, no, it's good. It's good now, actually.
Good?
Yeah.
I was just saying that I'm nervous for the exam.
Mm-hmm. Mm-hmm.
But I mean, I've been practicing, so I think I'll be fine.
That's good. I think, at least from experience, I've just come to like know that the best way to sort of prepare for like sort of these exams and stuff is basically just practice. Like calculus is something you can just like learn overnight. It's like working the problems, sort of like getting comfortable with all the different kinds that you guys are sort of gonna be encountering, things like that. So yeah. So I think that's pretty much the best way to do it is just like sit down and really just, I mean, it sucks, but just sort of sit down and sort of like be like, okay, just try to figure out like, okay, all the different kinds of problems. I always like to say like for each sort of section, there are different types that they sort of show you, that they sort of give you. The first one I want to go over is like the one with like the piecewise function. It's like there's a constant in one of the functions, and it's like okay, find the constant such that it will be continuous, right? That makes sense. So that's just like one example of something like that. So yeah, and there's like a bunch of different types for that kind of stuff. So like just going through like your textbook and like looking at the practice problems. You don't have to do every single type, every single one for each type because they give like 10 sometimes, but just generally going over like yeah. Okay, sorry I already told Marissa this, but I just forgot to set my availability at academia. Totally my fault. Sorry if there was like some confusion there, but I think I've got it all like figured out. So today I just basically wanted to go over. I had an idea of like some stuff that I want to cover, some practice from problems from the practice exam that I sort of gave you guys. But before I do that, I would totally prefer if like you guys sort of had ideas like you're maybe like still a little uncomfortable with, and I could try to figure something out to go over something related to that.
I was like doing the 3.3 homework and I was kind of struggling with like tangent lines and stuff. I don't know if that's like what you were asking.
Okay. So cool thing, 3.3 actually won't be on the exam because it's like so the exam only covers modules 1, 2, and 3. So that's only like through continuity.
Okay.
So I think you should be all good. I can help with tangent line stuff in the future. But right now, just because of like, the midterm coming up, I want to like focus on stuff that's sort of like from this first 3 modules. If that makes sense.
Yeah, so I won't have to worry about like derivatives and stuff for this term.
No. So I know that on the practice exam I gave you guys, there were like some questions about differentiability, things like that. There should not be anything about that on this exam. However, when Bradshaw emailed me about some things that I might want to cover, differentiability was a type of thing in there, but that's more like a concept that's basically like, okay, is it continuous and does the limit exist? Therefore, yes, it's good. So that's pretty much like the one thing they might need to sort of be watching out for. But you really shouldn't have to be too worried about like finding like the derivative through like the limit method or even any like any of the rules that we sort of like covered in lecture so far. And also, I mean, you have like a while to complete the exam, and it's open note, so you're not going to encounter anything that you haven't encountered in lecture 100%. So you should have notes on it if you've been sort of like attending that kind of stuff. If that makes sense.
Yeah, I also didn't really understand like the inverse trig function that he mentioned in review. That was another thing.
Yeah. I have something. That's definitely on my list of something to do. I might need to like look up a practice problem real quick for it, but I think I can explain like how to sort of understand all that. Yeah. Okay, cool. Does anyone else have anything that they want me to cover? I can definitely start with inverse trig stuff. I just might need to like sort of like do some digging to find a problem like real quick, unless everyone has like one just like sort of on them. It's cool if not. Okay. Sorry. Okay. So I'm just gonna like sort of try to quickly find. Okay, actually, I can just like sort of explain what inverse trig functions sort of are in general. I think the best way to think about them is to sort of start from the normal trig functions, and then you're basically just like working backwards in a sense. So by that I mean I only think a few of you have sort of like gotten my like unit circle sort of spiel. I can go over that again if any of you want me to, because I think I have a pretty good method of sort of like getting like trig evaluations like pretty quickly. Is that something that we might want to go over? I know Lily like shake like nodded her head because I can do that really quick and then I can sort of like
Yeah.
rework. Okay, so unit circle. This is about to be a really bad circle, guys. Okay, that was terrible. Okay, so hopefully you can see this like semi well. So the main three sort of like angles that you guys need to worry about are like the one at like the at the 30 degrees right here. There's the 45 and then the 60, right? So if I just like draw this out, it's sort of like this. Okay, wait, I'm not gonna. Okay, yeah, okay. So the way I like to think about it is like these triangles. I guess I can do this. Sorry if this is like really cluttered on here. Okay, yeah. So there's like a triangle here. There's like two triangles here, and then a triangle here. Can you try to like see that? I'm sorry, it's like very cluttered. But if I just like sort of like take these triangles out, there's one that looks like this. There's one that looks like sort of looks like this, and then there's one that looks like this. So don't. Okay, I'll draw this. Right. And so again, these are at like the 30 degrees, 45, 60. Can someone tell me like the pi, like the radian equivalent equivalencies for these different angles?
Pi over 3, pi over 4, and pi over 6.
Yeah, exactly. Cool. So the way I like to think of it is when you get, for example, like you see some kind of trig function evaluation thing. So such as like, let's look at sine of pi over 6. I like to associate each different trig function with either a y coordinate of one of these triangles, or in the case of cosine, the x coordinate of where these triangles lie, sort of like in the unit circle space, sort of like on like the xy plane, like cosine. You can just do pi over 6. Oh, yeah, pi over 6. Okay. So what do I mean by y? So like usually like sine corresponds to like the y coordinate, and then cosine to the contrary would be like the cosine part of it. So if I take a look at, sorry, I don't know like how to best sort of stand for this. Each of these coordinates, they're always going to be like the same distances depending on like the triangle. So since this is only like a 30, that's like a 30 degree triangle right there, and then this is also like 30 degrees right here. So this triangle sort of corresponds to like where the pi over 6 is, and then this one sort of corresponds to where the pi over 3 is. So it's sort of like, okay, so you have two that are sort of going up like this, and it's sort of down like right here, and then you also have two that are sort of like right here, and then sort of right here. And so you might notice that like these two triangles are pretty much the same, they're just oriented differently. And then what I like to do is sort of like look at it depending on the which side is sort of like the shorter side, which is like, okay, it's like this one and this one, right? I can draw this better. Like that. So this side, shorter side, and then this side, this longer one would be like the longer side. And those are each sort of like the components of the hypotenuse of like the main triangle that sort of goes from the center out towards the inner, out towards like the rest of the unit circle, right? So just something like sort of like a rule is that, and it sort of deals with like all of these like ratio things of how the unit circle is just like a length of 1. But I don't really ever think about like the ratios and that stuff. I just like to think of like short side is always going to be 1/2. And then the long side is always root 3 over 2. So I use this by say I get sine of pi over 6, I look at sine, I'm like, okay, y coordinate, just like instantly, just like I'm only looking at up and down. I look at pi over 6, I figure out where, like, which sort of like little tick mark on the unit circle I'm looking at. So I think of pi over 6, I think of 30 degrees. So I think of this one right here. So I normally like draw a little thing, like a little circle, and be like, okay, it's like here. And then since I know it's sort of like closer down like this, I'm like, okay, I know it's this, it's going to be this triangle. And since I know I'm looking at the y coordinate, I know I'm looking at the short side. And since I'm looking at the short side, I know it's 1/2, right? Does that sort of make sense?
So like,
And then,
will the short side like pretty much always be y?
so the short side is only y if you are at like this pi over 6 or this 5 pi over 6. So like right here, all of these tick mark places, right? So that's when the short side is a y. But when you have up here for like pi over 3, or what is that, like 2 pi over 3, or down here. Sorry, those are like not like accurate, but like this generally I'm trying to exaggerate their locations. That's when you have this triangle. And so it's the exact same. So this is going to be 1/2, but it's just on the x coordinate, right? Whereas this is on the y. This is the y coordinate. So if I have cosine of pi over 6, it's going to be √3/2 right here, right? But if I have, say, sine pi over 3, I'll look at sine. I'm like, okay, actually, I probably would look at the angle first. So I go to my little unit circle drawn out right here. I'm like, okay, I'll mark this tick mark right here. And then I know it's going to be this triangle. And I look at the y coordinate. And I'm like, okay, √3/2. Cool. So that's how I sort of like think of it. Does that sort of like make sense?
Yeah, kind of.
As like a method? Because when you sort of like get the more practice with this, it really starts to become like very, very snappy, where you just kind of like picture the unit circle in your head, make the little tick mark, and you just kind of like figure out which triangle it is. And then you only look at one component or the other, either that like up and down component or that the side to side one, right? So this is mainly what you're going to be dealing with. If you ever run into like a pi over 4, 3 pi over 4, or any of the ones sort of in the center of like with the 45-degree angles, these sides are always √2/2 no matter what. Always √2/2. So if you run into, again, like cosine of 3, so cosine of 3 pi over 4, since it's over here, you sort of have to like flip your triangle around, and you know that it's going to be √2/2 because it's 45-degree angle, but because it's like in the opposite direction towards like the left side, it would be negative √2/2, right? So like these are the easiest to deal with because it's always going to be like positive, right? But then when you have it sort of like down here, so this is 7 pi over 6, right? So if I wanted to do cosine of 7 pi over 6, that's an awful pi. That's also an awful 6. So cosine of 7 pi over 6, can someone like tell me, like take me through how they'd like figure this out?
Well, wouldn't it, since it's in the third quadrant, wouldn't the cosine be negative, and then the y would also be negative?
Yeah.
So
Yeah. So what's the value of it?
is it negative 2 or √2/2?
So the √2/2 only corresponds to like 3 pi over 4, pi over 4, 5 pi over 4, and 7 pi over 4, which are
Oh, so then would it be negative 1/2?
So
Oh,
remember that we're looking. It's okay. We're looking at this triangle here, right? We're looking at this
Yeah.
triangle, but it's sort of like flipped upside down. So it's like it's more like this. And remember, this is 1/2, and this is √3/2. And we're looking only at like the x component of it, right?
Oh, so it's √3/2 then, negative, right?
Yeah, but remember, negative. Sorry, you definitely like can't see it, but it's negative because it's sort of in that opposite direction. Whereas like this is the circle, and then here's like your
Yeah.
It's kind of like this. Okay, that's awful, but you know what I mean. Sorry.
Okay.
So yeah, so like that's sort of like my method of how to fix it. And again, like if you literally just like spend some time like sort of like looking at like, okay, like sine of like pi over 3, and then you just kind of like picture in your head, and then it's just like, oh, okay, it's root 3 over 2, and just like keep like running into those. It's like it becomes pretty snappy. Okay, so for tangent, I basically just do this exact same thing, but make it like a fraction. And then just put like, I basically have to divide it up into like its sine and cosine opponents, because tangent of, I can't see, tangent of x, I don't know how to draw this. Tangent of x equals one, like sine x over cosine of x, right? And so I basically, so if I was doing tangent of pi over 6, for example, I'd figure out what sine of pi over 6 was, which is 1/2. And then so I put 1/2 in over here, and then cosine, which is root 3 over 2, I put that down here. So like it would be a tan of pi over 6 equals sine pi over 6. So I feel like I can't see. And then that would be like 1/2 over root 3 over 2. And then I just do some like simple like drawing, like algebra stuff, not even algebra, just like arithmetic to, multiply. So to bring this out, because 1/2 over root 3 over 2 is the same as like multiplying it by 2 over root 3, right? So then it's like 1/2 times 2 over 3, and then that's just 1 over root 3. And you can like simplify this to be like root 3 root 3 over 3, but like that's, or whatever, or root 3 over 3, but that's like irrelevant, right? So that's sort of how I do tangent. I just had to like split it up a little bit. It's a little bit harder, but the rest of it, like sine, cosine, that makes it a lot easier, right?
Okay, thank you.
Sure. So to sort of like go into I'm gonna erase all this just so I need some more room. To sort of go into the inverse ones. Inverse ones, you have to think of like when you're given a question like what's the arc sine of 1/2? You have to think of it as like this basically represents an angle on this, right? Because when you're doing sine of pi over 6, you're given an angle, and then you're applying a function to it to then get some kind of like value based on like the ratio of like some like triangle stuff. It's weird, like right triangle stuff, right? Whereas when you do an arc sine, you're sort of like undoing that ratio to see like what's the possibilities of like sort of the different values that make up a triangle, or specifically to get like an angle like this, right? So what I'm trying to do with arc sine, or you can, this is also like sine the -1 of 1/2, right? Sorry, that's like awful. Either way is fine. I just like writing arc sine because it looks cool. Again, you're trying to find an angle out of it, right? So I think so. Like, sort of basing on this whole like arc sine thing off of what we've done with these triangles, what might be a good way to figure out what the evaluation of arc sine of 1/2 is. So they're never going to give you any arc sine thing that are like inverse tangent function or tangent function for them, or inverse trig function or trig function for that matter, that you aren't able to just like somehow evaluate. So when they give you this, they're always talking about, okay, whatever's inside of this inverse trig function is going to correspond somehow to one of the answers sort of like over here, right? So you can see that we have a 1/2, right? Right here. So you just have to think about, okay, if I were to create my own problem, including some kind of sine function, to then plug something into that sine function, how would I get to this 1/2? So it's sort of like, okay, sine of theta for an angle equals 1/2, right? Because we're basically right. It's basically the exact same thing as this, except we're sort of equating this to theta, right? And then just like applying sine to this, and since they're inverse functions, they just sort of like that goes away, and then you have sine over here, right? Okay, so we're basically thinking about, okay, what value of theta, what angle on this unit circle are we looking for to then get to 1/2? Marissa, did you say something?
No, I'm just thinking.
Okay, you're good, you're good. So let's sort of like see what we have on this unit circle, right? So, okay, we know we're looking for sine, right? So we know we're dealing with arc sine sine. So that corresponds to y component, right? Okay. So what are the triangles? What triangles do we have that get us the y component of 1/2? And to an extent, what angles on this unit circle make us think of the triangles to then get us the y component of 1/2? So we have this one, right? So what kind of angles correspond to this triangle? We have this one right here, right? And this one. I'm gonna try to get another marker. Sorry. I want to be more colorful. We have this angle, right? This one. This one. This is also, these ones are also lengths of 1/2, but we're not trying to find the arc sine of negative 1/2. We're just trying to find it of 1/2, right? So these aren't okay. Like, no. Like these ones, those are okay, right? So how should I say this? We know which triangles, which points on the unit circle we're looking for, right? So we know which angles we think would we could plug into sine so they get 1/2, right? So we're looking at pi over 6, and this is pi over this 5 pi over 6, right? Because I mean, if you go into your calculator and have it on radians mode, if you plug in pi over 6 or 5 pi over 6 into sine, then that will get you 1/2. So it's basically like, again, we're trying to find an angle that we can put into sine to then get whatever this inside of the inverse trig function is, right? And so we have two answers, right? But we also sort of have more than two answers. We have also like 2 times, we have 2 pi plus pi over 6, right? I don't know what that is. It's like 15, or it's like 13 pi over 6. And then I also have 2 pi plus 5 pi over 6. And so it's like, it's kind of like infinite in that sense, right? Because if you look at the what's the word? At the graph of like sine specifically, actually I can show you. I'm gonna like share my screen just real quick. Okay, so if I show you guys sine of x, shoot, that's not okay. Yeah, there you go. It sort of goes on forever and ever, right? So like there are infinitely many values that we can plug in to sine of x to then get a value of 1/2, right? But if I do arc sine of x, mathematicians have sort of like defined this to be, the only points where it would exist, because anywhere else, okay, so if this function didn't cut off, so that could be a function, you guys know what the rest of it would look like? Because it's the inverse, it sort of has that like mirroring effect, right, across like this like xy axis. So what it would actually look like is it would be more like exactly like the sine wave, but in a vertical direction, right? But that wouldn't be an actual function, would it? because it breaks the vertical line test, because you plug in one X value and there's like a bajillion, there's infinitely many Y values to get out of that. So they only define it for a very specific domain, right? So if we go over to like 1/2, I just had it. You can see they like for 1/2 it would be pi over 6, right? But we also said it was for it was 5 pi over 6, right? But 5 pi over 6 would be somewhere closer to over here, and that's not like defined within the arcsine like range. So you have to think of it as like how should I say? Inverse trig functions have sort of like a more limited scope of what they're sort of like dealing with in a sense. So I would normally always go with when you're trying to do these with the values closest to 0. So like don't think 5 pi over 6, think 1/2. If you're doing negative 1/2, don't think 7 pi over 6. Think negative pi over 6 instead, because you can also like do that by sort of, right? Yeah. Does that sort of like make sense? I just want to be like talking my ass off.
How do we know what the restrictions will be on the graph? Like what part of it is being analyzed?
Yeah. For sure. So I'd be surprised if they sort of just didn't sort of like explain like, okay, on the domain of like this, what would it be like? Because they normally, especially when you're dealing with like inverse trig stuff, they like to define what kind of values you sort of want to look at and what sort of you want to sort of hone in on. And I mean, like you could always just like literally plug into Desmos like, okay, arcsine x, arc cosine x, arctangent x, and then like look at what those are, but at the same time, like that's tedious and like something that you have to like, sort of like memorize, and that's sort of lame. So I understand if you like don't want to do that. But again, I think like being as close to 0. So like again, I think for that it was like pi over 2 to like here, right? To like negative pi over 2 for sine. And so my guess would be that cosine would just be from like 0. Most likely it'll be from 0 to pi. I guess I can like plug it in. Yeah, and if I share my screen real quick, you guys can see that it's only defined. It's only defined from. It's from negative. Interesting. It's from. Oh yeah, that makes sense. Negative 1 to pi because okay. So that makes sense because your cosine values over here and here are 1 and negative 1, and so therefore like when you're sort of like trying to get that out, because this is 0, this is pi. So then like when you're like, okay, so like, I know this value over here of cosine is of cosine of pi is negative 1. Therefore, like when you do sort of like, okay, what is the arc cosine of negative 1? Sort of you get pi like out of that. Sorry, that was really confusing and poorly explained. I understand. I'm trying to like think. Okay. So you guys started having trouble dealing with like where to specifically like look for it, or like the idea of how you're sort of trying to get an angle from a value out of the function itself.
I'm just so unclear about like when we would know that it was 5 pi over 6 versus just pi over 6 for arcsine of 1/2.
Yeah. So the mathematicians who have like created this arcsine of x have just sort of been like, the domain of this function is only from here. Does not include the 5 pi over 6 value. So when they say that like, okay, it's only from, what was it? Yeah, it's only from, you can only plug in values of like -1 to 1. That means you can only.
Okay, so we won't be given problems where it's possible for the answer to be 5 pi over 6.
No. Like
Okay.
that would literally like, that won't happen because like you can't get because 5 pi over 6 corresponds to like 1/2. And when you plug in 1/2 into arc sine of x, over here, or arc sine of 1/2, right? But that's already covered by pi over 6, and you can only have one output for a specific input. So if I plugged in arc sine of 1/2, I'm not going to get 5 pi over 6 or like 2 pi plus 5 pi over 6 or anything else other than just this one.
Okay,
So-
thank you.
So again, it's like as close to like 0 as possible. It's kind of weird with like how the domain and ranges work, but like that's not really something you're going to be dealing with. The most you'll see of inverse trig functions on the exam is like if it's just in like, okay, evaluate this statement to like get a value of x for which it works. Like literally, I can't imagine you guys running into like anything else other than that, honestly. Again, like the more problems and stuff that you run into, you can write that all into your notes, and then like all those rules you won't really have to like memorize because it's sort of like written in your notebook, right? That makes sense. Yeah, and then for like arctangent, again, I sort of like think of it as like I know he sort of did something similar in class, literally just like the other day. But I like to do something where it's like basically the exact same. I think that's how it works. How do I say this? For me, for arctangent, I basically am just like plugging and chugging. Honestly, I'm like trying to look for different, like which ratios, like which of the like √3/2 and 1/2, like which should go on top. Because that's mainly the only times that you'll be dealing with that. Because when you see an arctan, the only times you're gonna get something from that, the only possible things that they're gonna show you for that are gonna be arctan of √3, arctan of 1/√3, or arctan of whatever √2/2 over √2/2 is, which is literally like 1, I think, right? These are the only types of arctangent things that you're gonna get. And the only types of arcsine things you're gonna get are like 1/2 or -1/2. And these could all be negative as well. It could be 1/2, -1/2, or like √3/2 or -√3/2. Or then like, oh no, sorry. Yeah. √3/2, -√3/2, or like √2/2 or -√2/2. Just because like we only have so many answers for these trig functions that we know of, right? And we just try to like, okay, it's like a pretty like limited amount. So if you literally like write into your notebook like all the possible values of all of these things, you won't really have to like memorize it, like considering the circumstances. But it's basically just about like saying like, okay, like what kind of like what function, how do I say this? Like which parts of the triangle would best go on top of each other so that like it ends up working out. Because if you have like 1/2 over √3/2, that simplifies into 1. It would simplify into 1 over √3, right? Because if I do over √3/2, it sort of like flips over, and you just get and then the 2's cancel out pretty much. I guess I can like write it out. So times 2 over √3. Because when you divide by like something, you're also like multiplying by the reciprocal. It doesn't really matter how you do it, and this cancels out. You get 1 over √3. And so if you find out that like, okay, so like this is 1/2, this works. You got to think of it as, again, the top of it being the y, because again, you're still dealing with like sine over cosine, right? So y and then x is on the bottom. So you think about, okay, so like 1/2 is y. Which triangle gives me a y value of 1/2? It's this one. Where on the unit circle does that triangle exist? Oh, it's at pi over 6. There you go. And therefore, I would know, like, okay, this one is the arctangent of, for example, 1 over √3 is pi over 6. And then for arctangent of root 3, it would basically be the opposite. So like it would be this triangle because these would basically be flipped over. And if you just flip those over, then this is also just going to be flipped over. And then it would have to be like, okay, wait, still this y would then correspond to like root 3 over 2. This x would correspond to 1/2. Which triangle has like the x of 1/2? There you go. Does that sort of like make sense? Because I know like inverse trig and stuff can be sort of confusing.
Like kind of, I don't know. The arctangent like is confusing me.
Yeah. It's really about what sort of just doing a bunch of, how do I say? I don't want to say it's just like guessing, but like again, these are the only types of arctangent things that you're going to sort of be running into, and it's all, and how I do it is all sort of relating back to like the short side, long side triangles, and sort of like knowing which one to do. How to say like, and sort of like knowing which one to be sort of like working with, because when you have arctangent, like the arctangent of arctangent of x is basically just like arc cosine of x over arc sine of x over arc cosine of x, and so it's sort of just like an it's sort of how to say, thinking about which again, like which y and x values sort of like plug into there. That makes no sense. Sorry, this is like yeah. So like when you're do you want me to like go over an example rather than just sort of like talking about this like theoretically? Just because like like this, I don't think like this is really like being very productive. Like, I'm sort of like talking about like how it sort of like works in my head, but it's sort of
Could you do an example, please?
yeah. I like need to find one. I just inverse functions. I guess it'd be sine. Let me just look for one really quickly. Okay. All right. Let me just erase like all this. So let's just try to like evaluate the arctan of tangent of negative pi over 6. Okay. So like what do we want to like first look at to
Which triangle it is on the unit circle?
yeah, exactly. So we think about it like this. Which triangle are we looking at? We have pi.
Right?
We have this one, right?
Yeah.
Yeah. Okay. Cool. So how are we gonna like sort of like figure out what the tangent of negative pi over 6 is?
Would it be like sine root 2 over 2 and then over cosine 1/2, and then you multiply it out?
Yeah, exactly. So like you sort of recognize like, okay, so tangent is a sine over cosine, so it'd be sine of negative pi over 6. This is an awful 6. Then over the cosine of negative pi over 6 as well, and then you just evaluate which these are. And as you said, the sine of negative pi over 6, which is right here on the unit circle, right? Because it's basically just pi over 6, but you're sort of going in the other direction, right?
Yeah.
Then that is what gets you your negative 1/2, right? because it's in that bottom direction. And then for cosine, it's the same because it's still in this positive direction. So then it's that root 3 over 2, right?
Yeah.
Okay. We have that. And then again, yeah, as you said, you sort of like simplify it by like flipping it
So
over.
it's -1 over root 3.
Exactly. Okay. So then we can sort of like take that and plug it into a arctan of -1 over root 3. And then when you're sort of faced with this, you basically need to find the combination of different sine and cosine outputs, and like which one goes on top, which one goes on bottom, that can get you to this fraction, pretty much. And we've sort of already done it. We've sort of already done it because we sort of started with the answer,
Yeah.
right? But you're given, okay, like -1 over root 3. So that means that I need like a root 3 probably on the bottom. And you know that sense, like, okay, root 3 over 2 and 1 over 2, those are sort of like always going to be, one of those is going to be on top, one of those is going to be on the bottom. The 2's always cancel out. So you sort of have to think about, okay, like which one of these should go on top, which one of these should go on bottom, pretty much. And then thinking about which triangle you're going to be looking at for that. Because when you're looking at this triangle, what were we saying?
Well, I was just gonna say, like, it's kind of making more sense. The example kind of helped.
Yeah. So when you're looking at like this triangle, you know that the y is always 1/2. So now the sine is always going to be on that top. The 1/2 is always on the top. Whereas in this one, it's the x that's the cosine, and then the cosine is always on the bottom for tangent, right?
Yeah.
But for here, it's like, okay, so 1/2, that'll be on the top. So if it was going to be this triangle, which is at like pi over 6, -pi/6, pi/6, and whatever that is, -pi/pi over 6, that's when that sine's on the top, cosine's on the bottom, so 1/2's on the top, and that root 3 over 2 is on the bottom. But we know that it can't be like either of those two, right? Because they're outside of that domain that we were talking about earlier.
Yeah.
So we're only sort of looking at these ones. So if we wanted to just say, okay, like maybe it's this triangle, maybe we're only looking at this one, then we know, okay, let's just try plugging it in to over here. And then you sort of like write it out, okay, that's on top, that's on bottom. Really a 2, sorry. And then you simplify this, right? 1 over 3. But then you realize, oh wait, I have a thing that's like missing a negative sign.
Yeah.
So you realize, okay, I need to make one of these negative, but only one. So which one do you think that would be? Because we were looking at like only this triangle, right? Which is at pi over 6. So we need to make only one of these components negative.
Yeah. Would it be the x?
Yeah. Well, so if we made the x negative, then that would make us go over here, right? And that would get us 5 pi over 6. And we want to say sort of like over here.
That's
Ish,
the y.
Yeah, so if you make it the y, so make it the y, which is the 1/2 part, right?
Yeah.
Then we get that negative pi over 6 that we sort of started with, which sort of like gets us to there, right? Because we know that this is the tangent, basically. It ends is if you plug in like tangent of negative pi over 6, this is what you would get to then like eventually solve and sort of evaluate it to this 1 over root 3. I guess negative 1 over root 3. And that's what we're sort of like trying to like undo, sort of. So it's really about like sort of like reeling it back, sort of like undoing like the application of like one of the trig functions, in this case like a tangent of, like the tangent. The tangent function.
Yeah.
Yeah, so I think like Bradshaw always likes to write it out as like, okay, so if you have like arctan equal of like -1 over root 3, you sort of like to be sort of like to set that equal to theta, right? You like to equal that to, I'm sorry if you like really can't see that, but you like to set it equal to an angle and then apply the tangent function to both sides. So then you'd have what, tangent of arctan of -1/3 over root 3 equals the tangent of theta. And then this cancel out to just get -1 over root 3 equals tan of theta. And then at that point, you're basically just searching for an angle on the unit circle that gets you to this value.
Okay, thank you.
Sorry, that was very long-winded. Are the rest of you guys sort of like okay with that? Okay, so we've been talking a lot about like trig stuff. I sort of want to talk more about like specifically like the calculus part of the exam. You guys can feel free to like message me with any questions on GroupMe. If you run into a problem that you're sort of like, okay, I don't really understand how this works, I totally understand. I can like try to like find some like video that you can like sort of watch as well. I probably like explain it better than I can, just because I don't know, like I just could not collect my thoughts very well. Okay, let's I want to do. Are you guys okay with me sort of going over some practice problems from like the practice midterm that I sort of gave you guys?
Could you say it again? I couldn't hear what you said.
Oh yeah, I was just going to go over some of the practice, the problems from the practice exam. I could probably get through like one or two.
Yeah, that sounds good.
So I was going to do 5, but you've like seen that a bajillion times. Kind of like this one number 10. So basically asking if the limit of f of x as x approaches 0 equals 2, and f of 0 equals 3, then lim as f as x approaches 0 of cosine of x times f of x is what? So do you guys know how you could like sort of like start to think about this? So I think the first thing is that you can sort of like think about doing is sort of like plugging things in, right? And this is basically just asking you about like sort of what you can do with limits. Because and basically there's like limit laws that you know. Because it's all about like, okay, so I have like the limit of x approaches a, f of x, and then also like g of x. I can add these, subtract these, multiply these, whatever. And then that basically will also equal the x versus a f of x, and plus subtract multiply by then like the limit. So if there's ever some kind of how should I say, operation between the like two functions within a limit, you can sort of like split them up into being their separate things, right? So we can sort of rewrite this, right, as being different. So this could also be rewritten as 0 x times x equal to 0 of f of x, right? So from here, there's really sort of like one sort of like train of thought, right? Because we've already been given the limit of f of x as x approaches 0, right? Okay, so you know that's 2, right? So now we just need this. Do you guys know what that might be? How to like start to solve that? So the first thing that I always do when I run into a limit statement is like just try plugging it in and see if I can get something out of it. So I could try just like cosine of 0, right? And so if you think about like the unit circle and recognize like okay, cosine is x coordinate, 0 is just like right here, right? On the right side of it. Then like sine doesn't go anywhere, it's 0. Unit circle is a circle with a radius of 1, right? So just like the point, the end of the unit circle, so that means it's just 1, right? It's sort of that distance. So it's kind of like a flat triangle. If you sort of think back to about like the method I sort of talked about earlier, that flat triangle that has like just basically just like it's like a length of 1. And that's sort of like also the same with cosine and sine at like these different points. So like up here, it's just sine of 1, like sine of pi over 2, just 1, right? It's just like straight up. Cosine of pi is just also 1 or negative 1 because it's in that direction, sort of just all the way, and then sine of what, like 3 pi over 2 or negative pi over 2. That's just your negative 1. So from here, we get that the cosine of 0 is just 1, right? And that works because like if you plug in like cosine of x, you can see, and we should know that cosine of x is continuous from like the entirety of its domain from negative infinity all the way to positive infinity, right? So that we know that we can take this limit and get a value out of it, like with no problem, right? And so you can just like multiply these together. Does that sort of make sense how I sort of like went about that? They throw you this f of 0 equals 3 to sort of like trick you to be like, oh, I can just like take this f of x out and then just plug 0 in and then get 3, and then this is 1, and then like you get 3. But no, you have to like always think about it with like the limit is much different from the actual value. So like if you were sort of like to look at a graph of f of x, this would likely be a time when you would have a like a function going like this, and then be like this, right? Because the limit's down here at 2, but the actual value is up here at 3. That makes sense? Or something like this, and then sort of starts up here, and it goes like that. That makes sense? Okay, we're sort of like out of time. So you guys can like head out. I'm gonna try to like figure out how to explain inverse trig better a little bit. So I can like sort of get back to you guys on that, or and if I can't figure something out, I'll definitely like provide everyone with like a resource for that. Just 'cause I know that's tricky, but tomorrow I'll probably try to go more into like the problem solving practices. If that makes sense.
Thank you.
Have a good one.
Thank you.